This lecture deals further with the topics of field of view and aliasing and introduces the topic of parallel imaging. It is best viewed after having seen the lecture on basic MRI physics called spin gymnastics, as well as the first supplement to that lecture, which is called supplement 1A. This lecture will discuss field of view in greater detail, in particular how it relates to aliasing and anti-aliasing strategies, and that will lead to an introduction on parallel imaging. We are first going to start with a consideration of the gradient subsystem. The gradient subsystem is incorporated into the housing of the bore. It is very large and extends well beyond the field of view of the body part that is being scanned. Here we can see that the gradient subsystem occupies most of the cross-sectional diameter of the magnet bore and most of the length of the magnetic bore. The question is, what happens when there is tissue outside the intended field of view? The answer is, it depends where it is outside of the field of view. So if your intent is to image someone's head with the field of view outlined in the yellow box, and there is either a body part or an extraneous substance outside that yellow box, where will it appear in the image and how will that data be handled? The answer is it depends on whether that extraneous tissue is in one axis or along the other axis. In the illustrative examples that follow, the convention that will be used is that X will be the horizontal direction and it will be called the frequency encoding direction. Y will be the vertical direction and Y will be called the phase encoding direction, as illustrated in this diagram here. Let's use an example of the head. In this particular example, we're going to use a field of view of 24 centimeters in each direction and a bandwidth of 32 kilohertz. So the gradient is shown in red at the bottom of the slide, and you can see that the gradient extends beyond the field of view that is intended. It extends nearly the full length of the bore of the magnet. And the frequencies that are created beyond the intended field of view exceed 16 kilohertz in one direction at the chin end of the head and 16 kilohertz in the other direction above the vertex of the head. If we now choose to reduce the field of view in the X direction to 20 centimeters and keep the same bandwidth, as is shown in this next diagram on the right, we can see that the chin is outside the field of view. As stated already, the gradients extend beyond the field of view. So this extra tissue now at the chin end of the head extends beyond the intended field of view and has a frequency of greater than 16 kilohertz. The way the system handles this is that a frequency filter excludes these frequencies from the image reconstruction, and they do not appear in the image. Let's take a second look at the same example. We have a field of view of 24 centimeters on the top and 20 centimeters on the bottom and on the right. And we have shown that the frequency filter will exclude all the unwanted frequencies that exceed 16 kilohertz above the top of the head or below the inferior end of the margin of the head at the chin end of the head. It would matter very little at the top of the head because there's no tissue out there that emits signal, but at the bottom, if this signal was not filtered out by the frequency filter, it would alias back into the image, an undesirable effect. To avoid aliasing, different strategies have to be employed in the frequency encoding direction and in the phase encoding direction. As we have seen in the frequency encoding direction, a frequency filter effectively removes the unwanted signal from the reconstructed image in the intended field of view. In the phase encoding direction, different strategies have to be used. One of the most common strategy is to put the shortest body dimension in the phase encoding direction to keep all signal emitting tissue within the field of view. Another strategy is to use parallel imaging, and that's the subject of the next set of slides. What happens when the field of view is reduced in the Y direction? We're going to use the same example as previously. We're going to examine the head, and we're going to start with a 24 centimeter field of view in the Y direction and in the X direction. We are going to then look at what happens if we reduce the field of view in the Y direction from 24 centimeters to 20 centimeters and keep everything else the same. So on your right, you see the new field of view, which is reduced in the Y direction to 20 centimeters. And we're going to keep the same bandwidth of 32 kilohertz. Next, we're going to bring in the animation that we used in the previous lecture on spin gymnastics of the spinning balls and look at what happens to the spinning balls in the bottom part of the intended field of view and just beyond the 20 centimeter field of view. Watch what happens to these spinning balls just beyond the field of view at the top of the image and at the bottom of the image within the intended field of view. As that video clip played out, you would have seen that the balls outside the field of view always had the same pattern as the balls at the bottom of the intended field of view. They always had the same frequency and the same phase. We now take the spinning balls in their end pattern, take a screenshot and bring them down to the bottom right of the image and take a second look at what happens. There's the screenshot, and if you look at the pattern just beyond the upper margin of the field of view and that at the bottom of the field, they are exactly the same. So electronically, these cannot be distinguished from one another, and the system handles it in the following way. It moves the things outside the field of view at the top, puts it into the bottom, and the field of view is cut off where it is intended at 20 centimeters. If we look at what this looks like in a real image, we see the following. The part that's outside the field of view is not shown in that location, but because the frequency and phase of the pixels in those locations is the same as the bottom of the image, they are aliased down to the bottom of the image, and that is the resulting image that we get with the aliasing shown at the bottom. Aliasing occurs when signal from tissue outside the field of view folds over or wraps around to the other side of the view. It is an undesirable effect, and it occurs when there's tissue outside the field of view in the phase encoding direction. Parallel imaging avoids aliasing, it decreases imaging time, and it maintains spatial resolution, but at a cost of reduced signal-to-noise ratio. It's generally accepted that for every doubling in decrease of imaging time, the signal-to-noise ratio is reduced by a factor of √2. Parallel imaging is not a specific pulse sequence. It is a generic method that accelerates data acquisition in the phase encoding direction by reducing the number of phase encoding steps. Acceleration factors are typically about 2 to 6, usually in the 2 to 3 range. Many different parallel imaging methods exist. All involve reconstruction and correction of data. There are two main classes of parallel imaging. The first is reconstruction and correction of the data in the spatial domain. Examples are sense and asset. And the second is reconstruction and correction in the frequency domain. An example is called GRAPPA. All parallel imaging methods require two or more pairs of independent coils with independent receiver channels. The signals from the individual independent coils are amplified, digitized, and processed simultaneously, or in other words, in parallel. The discussion here will be on the spatial domain class, for example, sense and asset. This is easier to understand and it is frequently used. There are 4 steps in this type of parallel imaging. First, there's a generation of coil sensitivity maps for every coil. These maps must be different for each coil. Next, there's an acquisition of partial case-space MR data for 2 or more pairs of these independent coils. Third, there's a reconstruction of the partial field of view images from each coil. And fourth, there's an unfolding and combination of these partial field of view images to achieve the final full field of view image. Let's look at a generic pulse sequence diagram as is shown here. The various lines on the pulse sequence diagram from top to bottom is what happens with the radio frequency pulse, then what happens with each of the 3 gradients, Z, X, and Y, and the data sampling during the frequency encoding step, and how the data is accumulated and placed into case space as shown on the right. Pay particular attention to what happens with the Y gradient. You will see that the Y gradient is incremented in steps, higher and higher gradients to fill each part in case space until all the phase encoding lines in case space are filled. Let's play this video. So there's the gradient Y applied, followed by the gradient X. Next, there's an incrementation in the Y gradient, and the same thing with X. Another line in case space is filled. Then the Y gradient is incremented again. And again, and it has to be incremented equal to the number of times as you want lines of spatial data in the Y direction or the phase encoding direction. The total scan time is the time between the phase encoding steps, called TR or the repetition time, multiplied by the number of phase encoding steps. The number of phase encoding steps is the main determinant of spatial resolution in the Y direction. And TR is one of the major determinants of image contrast. Can you go faster without reducing spatial resolution or changing image contrast? The answer is yes, faster is possible, but there is a penalty. There always seems to be a penalty of some type with MRI. Remember that total scan time is equal to the number of phase encoding steps multiplied by the repetition time, which is the time between these steps. So if you want to acquire 128, 256, 512, or even sometimes 1,024 phase encoding steps, it's going to take a long time. What happens if the number of phase encoding steps are reduced? These next few slides will be more clearly understood if you have seen the lecture on spin gymnastics and the supplement to the lecture called Supplement 1A. These next few slides are going to go through the spatial encoding process in the Y direction and the consequences of various alterations in that process are made. The phase encoding process typically fills case space in a series of lines, starting often with ky equal to minus n through a series of steps, each step being equal to each increment in the phase encoding gradient through ky equal to 0 up to ky equal to positive n. The number of lines between minus n to plus n, or 2n, determines the spatial resolution in the y direction. For example, if n equals 128, the spatial resolution in the y direction is 128 plus 128 equal to 256. If n is reduced to 64, the spatial resolution drops to 128 in the y direction. The separation between any two lines in k-space in the conventional spatial encoding or scheme in the phase encoding direction is called delta k. And delta k is equal to 1 over the field of view, or in other words, the field of view is equal to 1 over delta k. The field of view is therefore determined by delta k, as inversely proportional to delta k. If you double delta k, the field of view is halved. Let's look at the same idea graphically using our animation model of spinning black and white balls. We're going to start first with the repeat of the pulse sequence diagram, which is shown at the top of this image. And as I play this video, watch what happens. For every increment in the y gradient, it's followed by the application of the x gradient and a filling of one line in k-space in the y direction. Then there's another increment in the y gradient followed by the x gradient filling by another line. Now let's draw our attention to the spinning black and white balls with the next row of images below the pulse sequence diagram. Starting from left to right, we have all the balls with the white faces facing us. As we move to the right, we apply a y gradient of proper strength and duration to achieve 2 pi phase difference between the ball at the bottom of the image and the top of the image, which is 360 degrees difference, or 1 complete revolution difference. Once 1 complete revolution difference accumulates, according to the Nyquist theorem, to avoid aliasing, we then go ahead and proceed to apply the x gradient, read and receive the signal, and fill the ky equal 1 line in k-space. Next, we go to step 2, which is the next row of images. This time, as we move from left to right, we apply a y gradient, which is twice as strong. And in this instance, we wait until there's 2 complete revolutions difference between the bottom row and the top row. And once again, we apply the x gradient, read and receive the signal, and fill the next line in k-space. We keep doing this until we get to the nth repetition, which brings us to the bottom row. As we move from left to right, we apply a y gradient which is n times as strong. The balls spin until there is n times complete revolutions of phase difference between the bottom and top row, so n times 2 pi. And if you look at the image, we see we have the maximum number of lines in the y direction once we get to this nth step. The x gradient is applied again. We read and receive the signal and fill the final line of k-space, the ky equal to n line in k-space. What happens when we skip steps to go faster? What are the consequences? What are the results? Well, if we skip this first step completely, where we waited for the bottom and top row to get 360 degrees out of phase before we turned on the x gradient, and went directly to the second row and applied a gradient twice as strong, such that we got 2 complete revolutions of phase difference between the top and bottom rows. So we've skipped that whole first step, went right to the second step, and we wait for 2 complete revolutions of phase difference to accumulate before we go ahead and do the X gradient and read the signal, and keep skipping alternate steps until we've acquired a total of n times 2 pi phase difference. The result will be we'll have gone twice as fast because there's only half as many phase encoding steps, and we'll have maintained spatial resolution because n is still the same number, but we'll get aliasing because we have violated that Nyquist sampling theorem. This is the desired non-aliased sagittal image of the head. However, if only alternate KY lines are acquired by skipping phase encoding steps, and we incremented KY by 2s instead of by 1s, with KY going from 2 to 4 to 6 up to 128, the data would be collected twice as fast, but the field of view in Y would be halved, and so we'd get something like that with the top and bottom cut off. But in addition to that, we'd get aliasing with fold over, and the result of the fold over would be an image that looks like that. Parallel imaging collects the signal in the KY direction by using 2 independent receiver channels at the same time, and it solves this aliasing or fold over problem with algebra, which is going to be illustrated in the next few slides. All parallel imaging methods require the use of at least 2 independent coils. In this illustration, we're going to use 2 independent coils, and the coils are going to be referred to as coil 1 and coil 2, or C1 and C2. They're illustrated by those brown loops of wire, one placed on the anterior surface of the head and one placed on the posterior surface of the head. During the process, coil sensitivity maps are acquired. This is usually done during the pre-scan portion of imaging, and this acquisition of these sensitivity maps is very fast. The images are very low resolution. Coils are most sensitive to the material which is closest to them. So in this schematic for coil C1, we've illustrated that the pixels closer to them are whiter than the pixels further away, and the opposite is true for coil number 2, where the pixels closest to them are at the bottom of the image. They are whiter than the pixels at the far end of the image. Parallel imaging requires the use of 2 or more independent coils. In this example, we're going to use 2 coils. We're going to undersample in the KY direction. That is, we're going to go to every second line in the Y direction by incrementing the phase encoding gradient twice as much as we normally would. This is going to reduce the field of view by 2 in the Y direction, and we'll get aliasing and fold over in the Y direction. So there's the reduced field of view. That's the aliasing that we get from one coil. This is the field of view from the second coil. That's the aliasing that we get from the second coil. When you look at the 2 images in the center of the image, these aliased images from coil 1 and coil 2, they look the same. They're very similar, but they're not exactly the same because they're influenced by the sensitivity profiles of each coil, which are illustrated on the far right. Each coil is most sensitive to the tissue close to us, and the signal it receives will be displayed as whiter, and that the signal further away from the coil is displayed as blacker. So when you see with coil 1, within the field of view closest to us, the pixels are whiter, and within the field of view furthest from it, the pixels are blacker. The opposite is true for coil 2, which is illustrated at the bottom of the image. So this shading influences the pixel values at every location within the aliased image from coil 1 and within the aliased image from coil 2. These differences between these two images are because of the sensitivity profiles of the two coils. And this difference is what allows the images to be unfolded using linear algebra, and that's going to be shown on the next couple of slides. This brings us to the math behind unfolding the image. This is going to be done by illustrating the calculation of the signal intensity values of 2 points A and B. A and B are 2 points shown in the unfolded image. Their true signal intensities at this point in time are not known. These same 2 points are mapped on to the aliased image from coil 1, which is at the top on the right, and from the aliased image from coil 2, which is the bottom on the right. These 2 points A and B are chosen so that they have the same X coordinate, but they have different Y coordinates. And their Y coordinate has been chosen so that in the aliased images, A will fold over exactly onto B. So A and B will be superimposed in the aliased images. Next, we don't know what the true signal intensity value is at point A, but whatever it is, we know that it will be influenced by the signal intensity profile of coil 1. The same is true for point B, an aliased image from coil 1. We don't know what the true pixel intensity value is, but we know it's going to be influenced by the signal intensity profile of coil 1 at this point B. Similarly, in the aliased image from coil 2, we don't know the true value of the pixel intensity at A, but we know that it's influenced by the signal intensity profile of coil 2 at this point, and the same for point B. So now in the middle, we place the aliased image from coil 1 and the aliased image from coil 2. We've chosen A and B, so when the image is folded over, they're superimposed on one another, and we can measure the signal intensity value at point P1 during actual MR imaging. So A and B overlap at point 1, and we can measure P1. So we know what P1 is. We know what the signal intensity of coil 1 is at point A and at point B. The only thing we don't know is the true values of A and B. The same is true of the point in the aliased image from coil number 2. So we can measure that value with coil number 2. And again, we can measure the true value of the intensity at point number 2. We know what the signal intensity profile is at points A and B, so we can write that second equation. So everything that's shown in blue font is known quantities. The only thing that we don't know is what's shown in black font, the values of A and B. Now it comes to the simple linear algebra. We have two equations with two unknowns, A and B. We solve the equations for A and B, and we can unfold these points. And then the computer does the same thing for every other paired point and is able to unfold the complete image. This brings us to the end. We have measured the actual signal intensity at every point in the aliased image of coil 1 and the aliased image of coil 2. We've combined those actual measurements with the knowledge of the sensitivity profiles of each coil. This allows the partial field of view images to be unfolded and combined, and this achieves the final field of view image as is illustrated here. There's the half field of view image, and then the unfolding, all done with the knowledge of the signal intensities in each of the aliased images and the sensitivity profiles of each of the coils. And that's the final image, unfolded and unaliased, achieved at half the time, but at a 40% reduction in signal to noise. This brings us to the conclusion of this lecture. In this lecture, I discussed field of view and what happens when the field of view is smaller than the body part being imaged and when tissue lies outside the intended field of view. The topic of aliasing was discussed in greater detail. Anti-aliasing strategy were discussed, and the last half of the lecture dealt with parallel imaging, demonstrating that it enables imaging to go faster while maintaining spatial resolution and solves the aliasing problem by the use of independent receiver coils and algebra, but at a cost of loss of signal to noise. There is a lot of literature on parallel imaging. An excellent review article, which I would recommend, is as shown here. It appeared in JMRI in 2012, and it covers the basics of parallel imaging, an explanation of the spatial domain methods, the case-based methods, and also discusses some clinical uses of this method.